So welcome to Haskell class lecture number 4. Just as a reminder, I won't be here on the 15th because I'll be going to Lambda Jam. But Wednesday's class is going to be moved to Thursday, the 16th, same time and place, 5:30 in this room. And here's the answer to the lecture 3 exercise. Sequence is, of course, the function that takes a list of actions and returns an action that returns that as a list. And the code for that is up there. So we have a base case where if the list of actions is empty, we return the empty list. We don't do any I/O. We don't do any actions, but it's in the I/O type. And if we have a list, then we bind in a do block x to the first action, x's to a call of sequence on the tail, and we return the cons. So is that code example clear to everyone? I take that as a yes. Mm-hmm. Okay, so what should we expect from this expression? And just to remind you, you can do fmap on an I/O, because an I/O is just another type of container. And when you fmap a function over an I/O, you get the I/O that returns the fmap, or returns that function applied to the result. So like if you fmap times 2 over return 4, you get an I/O that returns 8.
Just print the first 5.
So you're thinking it's going to print the first 5 numbers. Yeah. Does anyone disagree with that?
So I want to print it 5 times.
Print what 5 times?
The same sequence of numbers.
Print a sequence of numbers because map print on that list is going to be a list of I/Os that do something. And then we're sequencing it to get a single I/O. Does anyone disagree with Peter? Well, I do, because he's wrong.
Oh, no.
The answer is that it doesn't stop.
Oh, that's right.
We don't benefit from the laziness because sequence is going to require all of the effects to occur before any of the computation is allowed to progress. So in this particular case, we're demanding an infinite number of side effects in evaluating that I/O. And even though, because of the fmap, we're only taking 5 things off the final list, we're still expecting the whole list of side effects, which is an infinite number, to occur. And of course, that means it's just going to continually print numbers and never stop. So on laziness, if there are any questions about it, you've all had some time for things to sink in. Is there anyone who's not clear about laziness and how it works?
I'm sure I'll have questions later.
Okay, great. So we're used to base types like int, where thunk evaluation is simple. But then we've also seen these infinite data structures where pieces of the data structure can be evaluated without evaluating the whole thing. That's why infinite lists work. You can take 5 off an infinite list and not have to load the whole thing into memory. So the important concept is WeakHeadNormalForm, but first let's talk about what normal form is. Normal form is a fully evaluated value. And in the base types, it's an element of the base type. And with a function is a first-class value, and it can't really be reduced anymore. Or it can be an element of a compound data type. So, you know, just the string cat, the tuple there, 7.3 and true, and so on. But with WeakHeadNormalForm, the first two cases don't change. So the base types are defined exactly the same way, and the same with functions. But it can also be a value in an algebraic type, data type whose fields may or may not be thunked. So in WeakHeadNormalForm, you evaluate the outermost constructor, but you don't necessarily evaluate the fields. So on the first example, we have that it's a cons, and then we have two thunks. In the second, we have that it's a just, but we don't necessarily have evaluated that string yet. And in the third, we know that it's a tuple, or a pair in particular. So that's why infinite lists work, is because when we're doing a take 3 off this infinite list, we do 3 evaluation steps where we say it's cons, and because it's a cons, I know that the next thing to do is decrement my n and call take on the tail. So take 3 on that thunk becomes cons 1, take 2 of a different thunk, and the end result is a list of 3 elements. And it doesn't have to evaluate those 3 elements, so I actually have those thunked. Of course, something else in the future may evaluate those thunks, and then they'll be forced. WeakHeadNormalForm is why the length of a list with an invalid value, 1 quad 0, is 1. You evaluate that 1 quad 0 thunk, and you're going to get a runtime error. But it never gets evaluated, because if we're only reducing the list to WeakHeadNormalForm, which is all we need to do to figure out its length, then it never gets evaluated. The seek function, which is what you use to force evaluation for performance or to prevent a space leak or a thunk leak, it doesn't dethunk the whole way to normal form. It only goes to WeakHeadNormalForm. So when we have this list with this invalid value in it, and we seek that, it doesn't cause a runtime error, because seek is only going to evaluate the list to WeakHeadNormalForm and say, yeah, it's a cons, but it's not going to go any deeper. Now in control.DeepSeek, that's a module that has a DeepSeek function that will go the whole way to normal form. So you have a value exactly like what I showed before, and with DeepSeek, it will cause an exception, because it's going to go down the tree. It's going to evaluate the whole thing. If you want to annotate a data structure's field as being strict, you can do that by prefixing it with the bang symbol, which is the exclamation point. So up here we have a pair that's defined as either being a lazy pair with the lazy constructor or a strict pair with the strict constructor. And then we have pair FST, which is like the FST function on a tuple, and we apply it to both a lazy and a strict pair, where the left value is fine, it's a 5, and the right value is an invalid thunk, 1 quad 0. And with the lazy tuple, everything goes fine, because that 1 quad 0 is never actually evaluated. It just stays a thunk forever. But in the strict example, it blows up, because the strict data structure requires that the thunks be evaluated. So now it's time to talk about the Prelude. That's the Haskell module that is implicitly loaded whenever GHC or GHCI runs. You can actually not have it load, but that's a language extension, which we'll be talking about much later on in this course. All the different language extensions that you can do. And that's where most of our familiar functions come from. Some of these don't. Some of these come from data.list. But most of these functions that I'm showing are in the Prelude. And the documentation is in this list here. It's worth looking at just to see what Haskell documentation looks like. A lot of it's type class related, which we haven't been over in detail, but we'll be figuring that out pretty soon. the next class is where we're going to dive into the type classes. Eq and ord are two type classes that you will see in this presentation. So Eq is the type class for things that can be checked for equality. Ord is a strictly stronger type class because it allows you to compare. It allows you to define less than and greater than. So here's some exercise. What kinds of types might not be Eq? If you guys have any thoughts. And secondly, what kinds of types might be Eq but not ord?
So maybe like string matching could be eq but not ord.
Why?
Because like is cat greater? Well, I guess they could do like the length of a string could be greater than the length of the other string, but
Or you could do alphabetical, which is what they actually do.
oh, all right.
Yeah. No, but that's okay. I mean, that's a start, right? Because there are languages, I'm thinking Java in particular, where they use length first before they go alphabetical. So your string comparison might not be alphabetical.
Use files would be eq but not ord.
Yeah, file handles are an example of that. So with regard to things that aren't Eq, the answer would be your function types, because function equality does have a mathematical meaning, but it's computationally intractable. Like f and g are the same function if they return the same value for all x, but for any interesting input type, quantifying over all the values is pretty much impossible. And an IO is conceptually a function, and worse yet, because the parameter is world, well, you can't actually iterate over all the possible worlds unless you want to generate a world where, you know, we're all cockroaches or something. So with regard to things that are Eq but not ord, Rob was right on handles. Also, we haven't covered IOREF, but it's a mutable cell that you can alter through in the IO monad. There's a meaningful definition of equality, which is if they are the same object. In fact, that's the only correct definition of equality because the state of the things can change. So, and you want your equality definition to be stable. With regard to ordering, you could use like pointer addresses or something and get an ordering. And in fact, that's what many languages do. I think that's what Java does. But if you do that, then your ordering is non-deterministic because you can run the same program and get different results for your ordering, which is obviously undesirable. So comparison functions look like this. You have ordering with these three constructors, LT, Eq, and GT. That is the result of a comparison. When you run compare on two things, LT means that the first argument was less than the second argument. GT means that the first argument was greater. And EQ means that they were the same. You have your math functions. So what I'm going to be doing in this class today is just blowing through a lot of the functions that you'll see and that you'll use. And don't worry if you don't remember all of them. It's just good to know what the capabilities are. So plus, minus, times. We've all seen those. They work on num types in general. Abs and negate. Quat and div are two integer division functions. They have different behaviors on negative numbers. I think div rounds towards 0 and quat rounds lowest. And then mod and rem are the remainder or modular arithmetic. I think mod is allowed to be negative when the first value, when the first argument is negative, but I would have to look that up. We have single slash division, which works on fractional types. That's your doubles, your floating points, your rationals if you load those in. We have the caret is integer exponentiation, and your double star is floating point exponentiation. So we also have integer conversion functions, truncate, floor, ceiling. We've talked about those before. You've got pi, which is a value that lives in any floating point type. The only floating point types that I'm aware of are float, which is the 32-point floating type, and double, which is what you'll almost always use for actual floating point. As we discussed, there's that legacy thing of the name double, which is a terrible name. We have our math functions, x, blog, squirt, sin, sine, cosine, tangent. The a prefix is just the inverse of the trig function. The h suffix is the hyperbolic, and you have the hyperbolic inverse. Then we have our various floating point identifications like is nan, is infinite, and is denormalized, which unless you're doing a lot of floating point arithmetic, you probably won't worry about the last two very often. Denormalized numbers are numbers that are so small that you're losing accuracy, and that's like around 10 to the negative 300.
Interesting. You can use it has infinite and not a number, like as part of a float.
Yeah, is nan. We'll check if it's a nan or not.
Okay. But so you can think like negative infinity or positive infinity as values. And you can have nan as a sort of missing value.
Yeah, they live in the floating point type. Yeah, that's IEEE floating point. There's also a -0, which is actually slightly annoying because it's a different bit pattern from 0, but it's equal. So just to show some functions you'll work with sometimes, we have id, we've seen that before. We have const as defined up there, and we have the $sign. So let's go through these exercises, which should be pretty easy. What do you guys expect for id 3.14? Anyone have
3.14.
Anyone disagree with that? No, it's 3.14. All right, const 21 but salute in a string. What do you guys think that's going to be? It's not a trick question. If it looks easy, it is.
Error?
Why an error?
Can it implicitly cast 21 to a string?
Does it have to? What's the type signature of const?
It's just 21.
Anyone disagree with 21? Yep. This is just memory review. What do you guys think the infix and the precedence level of the $sign are? If you haven't seen it, then I would not expect you to know it, but 0, and it's left or right associative.
Right.
That's correct. And then what do you guys expect for show squirt 25?
Five is a string.
Close.
Oh, 500.
Yeah.
The square goes to float.
Yeah, because it's a floating point.
It's a num to float.
It works on floating point. Floating is a subtype of, yeah, it's a subtype of num.
But it only takes floating input.
Exactly.
Okay, so it's like floating a, fat arrow, A to A.
Exactly.
Okay.
Okay, so another thing you'll see a lot is section syntax, which is where you have an infix operator and you specify either the left or the right argument, and you get a partially applied function. So there are examples on the left of what it looks like. So question is, what do you guys think the type of times 7 is going to be?
It's the num A to A.
Num A, fat arrow, A to A.
Yeah.
That is correct. What do you guys think the application of times 7 to 11 is going to be? Anyone disagree with 77? Yep, it's usually the easy answer is the right one. Map 2 to the over 1 dot dot 4. 1, 2, 4, 8. Anyone?
2, 4, 8, 16.
Anyone disagree?
The 0.
That's correct. All right, so what do you guys think this one's going to be?
8, 7 cubed.
I'll accept 7 cubed for the middle one. 8, 7 cubed, and 5. Anyone disagree? Do you have a question?
No, what's the point of constant? Or is it, sorry, const?
Uh,
It's just, because it seems kind of useless, like it returns. It takes, maybe I'll just think about it.
no, that's a great question. So the use of constant is that sometimes you have a value that may depend on a condition or it may not. So you have an API that takes a function, and sometimes you want to, as the person using that API, sometimes you want to just say it's always 5, but the API takes a function. So you say, okay, I'm just going to pass in the function that always returns 5. So we're actually going to see that a lot when we get into type classes and we start implementing various type classes, and we'll often see cases where we just want to ignore a value. You know, we have to accept it to conform to an existing API, but we just want to ignore it.
Okay, thanks.
But yeah, you guys were right with 8, 7 cubed, 5.
So is const id a arrow a?
No, id is a arrow a. Const is a arrow b arrow a. Takes an a. It takes an a. It takes a b. It ignores the b and returns the a. Or another way to think of it is it takes an a and returns the function that just ignores its input and returns a. It returns a constant function. And for those who are familiar with the K combinator, that's what it is. A much better combinator than Y combinator, since it hasn't been hijacked by the venture capitalists yet. Okay, so the dot is function composition. And that's how you compose functions. And it's from right to left in terms of time ordering. So f.g is the function that does g first and then does f to the result. And flip is another one that you'll see often. It takes a 2-argument function and returns a function that is very similar but operates with the arguments flipped. So what do you guys think this first value is going to be?
21.
Anyone disagree? That's exactly right. This isn't really an exercise. The info on the dot is it's precedence 9, so it's actually a much tighter precedence than the $sign. The associativity actually doesn't matter unless there's another infix level 9 involved, because function composition is associative. Otherwise, group theory would just be screwed. What do you guys think this one's going to be?
21 squared is.
21 squared. Any disagreement? Now go with the easy one. All right, what do you guys think this is going to be?
House cat.
Here in house cat. Anyone think it's going to be a type error?
Oh. I don't.
No one thinks it's a type error. That's good, because it's not. And what's flip map?
What's the type signature of map again? Just A to,
So it takes like a function list.
let's see like the exact.
Yeah, it's
There's no type class restrictions.
Oh, that's really.
that's the type signature of map.
Fat, no double bar. Okay. Cool. Yeah. So it's just bracket A to an A to a B to a bracket B. A to the B.
Yep. List of A to A arrow
Maybe
B.
never had that.
It's a list of B's. That's correct. Another thing you'll see sometimes is undefined. That is failure. It's bought. It's going to give you a thunk that throws up whenever you evaluate it. So until now, I've been using 1 quad 0 as like thunk that blows the world up if you evaluate it. Undefined has the same effect. You often use it when you want to test that your code compiles, but you have parts that you haven't implemented. You shouldn't be using it in production because it will crash with a runtime error if you try to evaluate it.
I see. So wait. So the idea is that you can actually put that snippet anywhere in your code, and it'll compile just fine.
Well, yeah, you can use undefined as like a function. So like, let's say that you have like a constant A defined, and you have something that takes a B and does stuff.
Yeah.
And you have a function A to B that's like really complicated. And before you implement it, you want to see if the rest of your code compiles. You could define that function.
Like in C++, if you give like a function definition, you have to then give an extension, give an implementation of it, right? But here you can give a type definition of a function, but you don't have to actually like
Right.
implement it for any particular patterns.
And it will compile.
Okay, that's interesting.
But it, I mean, I would say that in like production code, you should just grep for undefined, and if you see it there, go yell at someone because it's kind of defeating the purpose. $bang has the same type signature as dollar and the same precedence ordering, but it's strict in the second argument. So it could be defined this way, x seek f of x, and as you can see, if you do const 0, $ undefined, because that undefined thunk is thrown away, because it's const, so it just says, I'm already returning 0, I don't need my argument, so I'm just going to throw it away. That's fine. But if you use $bang on the undefined, you know, const 0, $bang undefined, because it's strict, it actually does evaluate it, and the world blows up.
What are some use cases for $bang over dollar in like practice?
Performance, because you saw the thunk leak example, right, with the fold L. Yeah, performance is a big one. You know, when you're writing high performance code, you often want to make large amounts of it strict, and $bang is a compact way of writing that. $bangbang, which is in control.DeepSeek, uses DeepSeek instead of seek, so it's going to evaluate it the whole way to normal form. So in our second example, we have a list with undefined in it, and if you $bang that after const 0, well, it's only going to evaluate that list to WeakHeadNormalForm, so that undefined is not going to get evaluated. But if you use $bang and it goes the whole way down and evaluates everything, then the world blows up. So now it's time to talk about list functions. There's a cat with his to-do list. My cat's to-do list is very different, much more of the knock stuff over. And the running around like an idiot is more like 10, 11 o'clock, because by midnight I'm already asleep and they realize that it's not going to annoy me because I'm fast asleep.
It's pretty good.
So we're going to expose ourselves to a lot of list functions because they're important, conceptually if nothing else. Lisp originally stood for list processor. It's where the name comes from. It's a common go-to collection type. Many of the APIs use lists. And we start working with larger data sets. aka big data up there. Thought I'd get a chuckle or two out of that. When you start working with large data sets or with event streams, you are thinking of data in terms of sets. And the list API is a great way to get started. Now, I'll readily admit that the linked list that comes with Haskell isn't a great all-purpose collection type. Your append, your elem, which is searching to see if something's in the list, your last, and your indexing are all O of n. So performance isn't great. You should prefer vectors if you're doing numeric work, preferably on box vectors. You should prefer set or map if you're doing a lot of lookups. There you'll get log n lookup rather than O of n. You want to prefer text over string if you're doing a lot of text processing, because text is just much better optimized. And you want to prefer byte string if you're working with blobs, which are large binary arrays. But for our purposes now, it's good enough. And not only that, but all the other collection APIs are heavily inspired by the list API, which is why if I showed import qualified, if I haven't, then just ask me about it. It's a way to import a module without bringing all the names in, because a lot of the other collections will have names that collide with the list function names. So let's start with length. We've all seen it. We know what it does. But here's something that might be surprising. It doesn't require the whole list to be in memory. Because of the laziness and the garbage collector, if you call length on this 10 billion element list, it will take a long time because it has to iterate the whole way down the list. But it will give you a result. It's not going to run out of memory. Map, we've all seen map. We know what that does. It evaluates the list lazily. So here we have a list which is 1, 2, and undefined. We map squaring, integer squaring over it, and then we take 2. And the reason that that doesn't cause a crash is because the result of the map is another lazily evaluated list. And since we're only taking 2, we're OK. Does that make sense to everyone?
I have a question about lists. Like,
Sure.
You can make an infinite list, or you can make this list that has 3 things in it. At runtime, is there a way or ever a reason to tell the difference between the 2?
Between a 3-element list that has an undefined in it
Like
versus...
like as a list that's of definite length versus a list that's potentially infinite.
Is there ever any reason? There's probably a reason. Unfortunately, I think cycle detection in lists is, I don't know how to do it. Because a linked list can have cycles, obviously. And if you try to evaluate the whole thing,
Let's go for it.
exactly.
What if you did take $2 it would still be fine, right?
Yes, it would still be fine because it would never evaluate that undefined thunk. But if you did $bangbang,
If you did map,
actually,
if you did map $2 bang 1, 2 undefined, then it would blow up.
well, it's interesting. I think, yeah, so if you do control.DeepSeek, so my intuition is that this is going to be fine, as we discussed. It is.
$bang is fine as well.
$bang is fine, but $bangbang is different because $bangbang will go the whole way down. So yeah, and of course, if that was an infinite list, it would never return because $bangbang says I want to, I want to go the whole depth. And if the depth is infinite, well then, too bad.
That's like a good way to confirm that you're not doing anything that's not collapsible.
Yeah, I mean the failure mode sucks because you'd rather get an error message than the program just hanging. But
Is there like a thunk stack trace?
there probably
trace.
is.
Thunk trace.
There That is a good question, and
Think outline.
yeah, I mean, I do want to spend a class looking at like profiling tools and some things like that, but I don't know the answer offhand.
People normally say $bang bang, or is there some?
I have no idea. I say it. You're right. It does sound kind of I don't know.
Better than your $! Exclamation point exclamation.
Exactly. So here's a question: is this a legal optimization for a compiler to do? This is map fusion or loop fusion. It's an optimization that can be interesting.
Doesn't depend on the types of, like, if F and G are, they have like IOs or something like that, right? If they affect other state, then it probably doesn't matter.
Okay, so that's interesting because computing an IO is not the same thing as executing it. So you can actually ignore the matter of whether the F and G return IOs. But your insight is correct. If there are no side effects, it's perfectly safe. If you're in a language where F and G are allowed to have side effects, then it's not safe. So yeah, that's essentially right. But returning an IO in a function doesn't mean that it necessarily has side effects. It means that it returns an action. And then when those actions get evaluated, there will be side effects. So the answer is that Haskell can and will do it. But in a language like Python, this is sort of a pseudo Python because I have an f.g there. It's not safe. It changes the order in which the effects occur. Filter is one that you've probably seen, but you pass in a predicate and a list, and it returns the x's for which the predicate returns true. And like map, you can use it on infinite collections and things will be fine. So we're taking 5 off filter even of an infinite collection, and we're okay. There's the fold family, which we saw in the last lecture. We've got fold L, fold R, fold L prime. We also have fold L1 and fold R1, which do not require you to specify an accumulator state. They will just take, for L1, it's the head of the list. For R1, it's the tail of the list, and use that. One of the compromises with that is that your function now has to accumulate into the same type as the type of the list. So if it's a reduced type computation where the accumulator type and the list type are the same, though, you can also use fold L1, fold R1, with the caveat that it will blow up if it's an empty list. With regard to folds in 7.10, you'll see a somewhat different type signature. Instead of seeing a list of A's, you'll see T of A, where T is foldable. Don't worry about that because the list type is foldable, so those functions are still going to work. They've just been given more general type signatures. You could, if you wanted, represent map and filter in terms of fold R. That's what it looks like. That's probably not how it's actually implemented, but it could be. We've got zip width and zip. Those are multi-list maps. So zip width takes a 2-arity function and 2 lists, and it will apply that function to the arguments in series. And it stops whenever either of the lists runs out. So for example, when we zip cat and the infinite list of integers starting from 0, as soon as cat runs out, it's done. And it gives you an indexed version of that list. Zip is zip with the tupling operator or the pair operator. And we've got zip and zip with variants for 3 up to 7.
Can we go back to fold really quick?
Sure.
Do we ever figure out the thing where you can pass a initial argument that's not the same type as the iterable?
I mean, yeah, of course you can do that.
Oh, you can't do that. Okay.
Yeah, you can.
I see.
Your accumulator type for fold L and fold R doesn't have to be the same type. And in fact, for many of these examples, like
Wait,
here,
no, go back.
okay,
Your A, right? The A on the left is the same as the A on the right. So is there something, for example, where you, let's say, that's a good example of this. Like, let's say you have a list of functions, and you have an initial value of type A, but after applying the functions, you're producing a value of a different type. That makes sense.
So you're taking
I
like
guess it's kind of a natural operation.
well, that sounds very dynamic-y because you can't do, if you have like a list of functions with different
Yeah, that doesn't make sense.
input and output
Yeah,
types.
that's because the first one, yeah, you have to have like a, yeah. Okay.
I think that like A, B, A list of B, A is like the A is the type of the accumulator, and then
Yeah.
A is the same output as the type of the accumulator, but it's like a list of B, which could be a type different
Yeah.
from A.
Exactly,
So you can accumulate into a type other than what the list is.
exactly.
But now with the list of you want the initial values. Like here, what if you start with an int, but you want to end up with a float? The int is your initial A, but the float is on the right. Like if you were like taking square roots, like iterative square roots or something.
Sure. Yeah, I
Just
mean,
cast or something and hope that for the best that's iterable.
no, you could do that.
So you can prove that it has to be a subtype. Actually, now that I think about it.
Yeah, so let's do fold R. You could have a function that is int arrow double, which could be like takes n and d and returns the square root of n plus d. Obviously, it has to convert the n to a float. And then you have an accumulator that's a double and a list of ints. So yeah, that would work.
Well, what if the B was a? I guess what I meant is, what if the B is a? Oh no, I see. Never mind. Okay, I was saying, what if the B is a double to a double, and then the A is an int, and
Okay.
the final output is a double. But that's fine because then you can't do that because then halfway through you reduce. Like the second step in you reduce, it would be expecting an int, but it would be getting a double, so it would just not compile.
Right.
I see.
Right. So yeah, so we have the plus plus operator, which takes two lists and appends them. Not very surprising. We have concat, which takes a list of lists and it just flattens them one level. So it appends all of the lists together.
Is there an arbitrary depth concat?
No, and that's another one that, so to do that for lists is impossible because it wouldn't be well typed. But you could do something like that with either a tree type that you created, where you could just have a flatten function that goes down the tree, or a traverse function. And traversable is a type class that I'll be talking about probably in lecture 8 when I get back from vacation. The other thing is that with type classes, you could say, okay, you can have multi-parameter type classes, which is going
Oh, I see.
also in the
So you have
second half
bound.
of the course. But you could do things like that. Like there are functions that like, you can use type classes to represent relationships between types if you use multi-parameter type classes. But that's not for a while. Catmap is a function that combines mapping and concatenation. If any Scala programmers are here, this is known as flat map. And it's exactly what it looks like. It takes a list, it maps your function that produces lists, and then it concats them together. We have null, which is a empty check. We need that actually because an arbitrary list may not have eq on it. Because if it's not an equality type, then the list, if A is not an equality type, then list of A is not an equality type. So you can't actually do equal equal empty list. You have to either pattern match or use this null function, which is defined as above. We have head, tail. A init is everything but the last element, and then last is the last element, and all of these are unsafe. They all hard crash on the empty list, which is usually not what you want.
What What is the difference between last and tail?
Last is the last element.
And it was tail everything except for the first.
Exactly. It's everything except for the head. So for alternatives to the partial functions on lists, you have the head may family. There's a last may, a tail may. They all return a maybe, which will be a nothing in the failure case. You also have the def family, def as in default, where you supply a default value, which is what it returns in case of failure. So last def 4 on the empty list gives you your default value of 4. But if you give it the list 1, 2, 3, I don't know why I put 1 dot dot 3. I literally saved one character there. You get a 3. You can also explicitly pattern match to similar effect. It can sometimes make your code more verbose, but you know what? Verbosity is not always bad. If it makes your code more clear, then verbosity can be a good thing. If your unsafe function is guarded by some condition that makes it safe, then just go ahead and use it, I would say. Like in this case, we're already, if we get to the head call, we've already validated that it's not empty. So we know that head is safe.
Isn't that susceptible though to like refactoring problems? Like if the if statement is more, if the structure is more complex.
It is, and that's.
Should you just write tests for that? Or is there
Well,
other ways to go?
it's a good question because I would generally say that this is for cases where you know that the Boolean condition isn't going to be refactored, or it's certainly not going to be weakened.
As usual, there's your argument. You should assume that
Everything can be
refactored.
changed. Yeah. In which case, just give up all hope because eventually your code will turn to shit, right?
Just use head may until they refactor that out too.
Okay. Right, until they're like, oh, I'm just going to erase this may because it looks like line noise.
Wouldn't you just got rid of the if altogether and just used head default and printed it?
For that particular case, yeah, you could. You could. I mean, this is just an example. But yeah, you absolutely could. The other thing you can do is just fail with a more useful error message. I mean, sometimes, especially in the I/O world, the only thing to do is crash. You're expecting a file, you're not given it, you just hard crash and say, here's what happened. Okay, so here's bangbang. It's the indexing operator in the lists. It's O of n, although it's O of n in the index. So, bangbang 0 will always be fast, and bangbang 1000 will always be, much slower because of the linked list implementation. So we see some examples up there. You shot me down, bang bang 0 returns the capital Y character. Bang bang 9, and you get the lowercase m. And if it's negative 23, it's like, well, that's a negative index, and that doesn't make any sense, so it blows up.
Are there amortized O1 like hash implementations of these things, or?
Yes, the linked list function is it's very easy to write recursive algorithms on, so it has a lot of didactic value and it's simple. But for high performance, you use something else. There's a sequence type, there's a vector type, there are all sorts of alternative data structures.
Is there an in-console way to show all the imports of a module?
All the imports of a module.
Like, can I just get a list of names of like the stuff that importing X brought into my namespace?
Yeah, you can try :browse and the name of the module. Here's reverse. Anyone need an explanation for that? Yeah, pretty simple. These are some more specialized folds that you'll see. And takes a list of bools, returns a bool which is true if they're all true, or takes a list of bools and returns the OR of all the bools.
Are those, I assume those are lazy and such, like, it will stop on,
They will. They will, which a fold L will not, as we discussed. So those will, any and all have the same property. maximum and minimum can't because they have to evaluate the whole thing. Sum and product, of course, are also strict, so they have to evaluate the whole thing.
What you did, infinity maximum,
Maximum of.
infinity and undefined.
Well, that's interesting because
Oh, it would probably be infinity, yeah. Like, oh, actually, I see.
So what if it was like?
Whoa.
I don't know, sorry.
That's true. No, if you're taking the maximum of a set that has like an upper bound, then when it hits the upper bound, it's done.
right, and there is a bounded type class, but I don't think it does anything smart. I mean, we can try that out. Like, let's do data foo equals.
How do you make it?
Actually, let's just
Yeah, how do you make infinity? I get not in scope data constructor infinity same.
1 over 0.
1 over 0.
Yeah, because it sees the slash and it knows it's not an integer type. So it. But if you do
Infinity declaration. They give us the current maximum.
so if you do
Yeah, but I can't do the. It's not working. You gotta. I think you gotta cast it or something. Oh, because they imported data type. You unimport.
yeah, so even on a bounded type, because Boolean is pretty clearly bounded, it only has 2 values. It's not smart enough to say I've gotten a maximal value and stop. So
Wasn't the dollar sign going to prevent the maximum from even running until it?
no, it runs. It runs. So
Yeah, I see.
Does it just affect how it?
yeah, I've created an infinite list where the head is true and everything else is false. And then I run maximum on it. And maximum true is greater than false. So if you run maximum on that and it starts with a true, you would want it to be smart enough to know that it's a maximal value, but it doesn't. It doesn't do that.
They probably, like whoever wrote the Prelude probably, I mean, they have full ownership of the implementation of that function or that type, right? So they could have done it without like having to figure out what the upper bound is for any partially ordered instruction, right?
Well, no, I mean, that's the reason that it's not done, I would guess, is because that trick that I'm describing only works on bounded, and that would add an additional type class constraint on maximum and minimum that doesn't always deserve to apply. Because floating point is not bounded. I don't think it is anyway.
Well, what I'm saying is they could have probably done like a bounded maximum and then had a type specific, had an implementation for those types that they knew were bounded, where they just call bounded maximum.
Yeah,
Like maximum equals bounded maximum or something.
we can
Just
take
a
this
bit more
offline.
request to ask about.
Haskell is broken.
No, I mean it's fine, really. You can always implement your own if you have like a special type and you say, I want to stop when I get a maximal value. So test your intuition. Is there a difference between or and foldle or false, where or is the double pipe?
Or is lazily.
It's not. Yeah, it's the non-strictness. Does anyone disagree with him?
I did not hear what you said.
Full L will evaluate the whole thing, but or will stop. So if you had like an infinite list.
Yeah, exactly. Fold L doesn't know when to quit, as I've demonstrated here. Now, there's a fold map in data.foldable, which uses what's called a monoid, which I'll discuss in the next class when I introduce type classes. And when you use fold map, it's a bit smarter. It will recognize based on the type that it will recognize when it's done. So if you want to take home exercise, you could implement each of these in one line and give me your best guess as to which ones you think are short-circuiting as opposed to the fold variants. Take and drop, take an integer and a list, and take returns the first n elements. And unlike head, it will not crash if it runs out. It just takes everything that there is and then empties out after that. So you can take 2,000 off this 5-element list. Drop will return everything but the first n elements. You have takewell and dropwell, which use a condition rather than a specific index. So in this first case, our condition is less than the character A. So 5, space, and capital C are all less than the lowercase character. So it takes those, then it gets to the lowercase a and it says I'm done, and it returns those 3 characters. If you take while const true, you're going to get everything because that's a function that's just returning true all the time. And drop while is similar, but it returns everything after the first failure of the condition, including that first element. We have one-pass pairings of take and drop, essentially split at. It's obviously not implemented this way. It could be. It returns a tuple of the take and the drop. But it does it in one pass, so it's more efficient. Span is the analog of take while and drop while, and then break is similar, except it's the inverse. So it will take while the function returns false, and then it will cut at the first true.
This is not most efficient. Oh, this is just like illustrated, right? It's not how
Yeah.
it's implemented.
Yeah, all of these illustrations where I implement a function, you shouldn't assume that the actual implementation looks like that. It's probably much more optimized. This is just the semantics of it. We have elem and not elem, which do a lookup in the list and see if the thing is there. So elem x and then a list is going to return true if there's an x in the list. Lookup treats a list of pairs as an associative map. It will return a maybe, nothing in the not found case. So we'll take maybe 30 seconds, probably not time to actually write this because we're already running low on time. But just think a little bit about how you would write elem using a fold and lookup using pattern matching. And just let me know if you think you're confident that you know how that would be done.
Race.
Almost done. Since it's already 7:20, I'm going to show the answers. You could do elem as a fold this way. Fold L, your accumulator is a bool, which, as you can see from the initial value, starts at false. And as you're going over the list, you update it with E or X equal to E. By the way, you may notice that I dropped the X's on elem. That's just a more terse formulation. It's in lambda calculus, it's called an eta transformation, but essentially, because of the currying, you can just say lme equals this function, and it's the same thing. And this is how lookup would work in pattern matching. You're looking anything up in the empty list is obviously false. You look E up in a list with, a list that has something in it, and it's a pair. And if the key is equal to that E, then it's true. Otherwise, you look up in the tail. And the pattern matching approach is faster because fold L is going to traverse the whole list regardless of whether it needs it, whereas the lookup is smart enough to stop as soon as it finds a match. from the pattern matching. It doesn't do a recursive call unless it encounters a pair where the keys don't match. Nub is the dedupe function. Just returns all of the uniques, and it tosses the duplicates and the triplicates. So
Where did they get that name?
I have no idea. It's not the best named function. I mean, there's unique, there's dedupe. Why they had to distinct? Why they had to call it nub? I don't know. Scanl and scanr are accumulate functions. These are a little hard to explain, and being short on time, I probably just skip the explanation. But what they do is, the concept is like a cumulative sum in statistics. You have an initial value, and then you produce the partial sums of the list up to that value. And scanl scans from the left, scanr scans from the right. Come and ask me if you have any questions about this.
So is it scan L with like +1? Just add 1 to each. Is that the same as a?
Exactly. It would start with a 1, so it would be 1, 2, 4, 7, 11, 16.
It's like, yeah, it's like 1 + 1, and 1 + 1 + 2, and 1 + 1 + 2 + 3.
Exactly.
Yeah.
So it's like a fold, but you get the output of each evaluation at the end.
Kind of. It's sort of like an unfold, actually. But yeah, it's an unfold based on the existing list. Cycle is the infinite lazy list. It takes your list X and it just returns the list that the infinite concatenation of that. So obviously, it's useful if you take something off of it. Take 10 of cycle 1, 2, 3, and you get 10 elements of the repeating 1, 2, 3 list.
Also useful if you want to print one output in your GHCI.
That's true. That's true. Repeat just takes one element and it cycles that element over and over again. Of course, a more finite function is replicate, which takes an integer, and I don't think it's defined this way, but it could be. Take n of the repeat of x, and that's just going to give you n x's in a list. And here's one of my favorites. It's iterate, or the unfold function, and you give it an initial value, or you give it a function and an initial value, and it will return the infinite list of x, f of x, f of f of x, 3 f's of x, and so on.
So you could use this to do like a 1-line Mandelbrot set.
I guess like a
iterate z squared minus c equals 0. Like,
yeah, you could do a
over and
Mandelbrot
over.
check. Yeah, exactly. And then sort does exactly what you'd expect. Actually, I probably shouldn't say it that way because it does something better than what you'd expect. It's a lazy sort. So if you only take 10 off of a sorted list of, say, 1 million elements, it's going to be n log k, where k is the number of things that you actually take.
What happens if you take A1, A2, and A3, where A1 equals A3, right? Or sorry, where let's say, okay, A1, A2, A3, where A2 is less than both A1 and A3, but A1 equals A3, but they're 2 different objects. It's just that under hoard. You seem like, is it sorting that preserves satellite data? That's what I'm trying to ask. Like, and you sort?
So you have 2 values that compare equal with their different values.
Yeah, will they maintain their relative order as if you had dropped everything except for the values that are
I believe so. I believe it's a stable sort.
stable sort?
Yeah, I believe that's true. Sort by allows you to give a custom ordering. And yeah, sort by compare is just sort. Sorting is using the default comparison that comes with the ord instance. And so for an exercise, which seeing as it's 7:25, this is more of a thought exercise, but how does one think you would implement a descending sort using sort by? Like what would you put in that my compare?
pattern match on the order and this return the inverse of it?
Return the negative.
Yeah.
Okay. So the negative of the comparison function. So what's the most, you guys are right. What's the most terse way of negating a comparison function?
When
Not.
Because not takes a Boolean and a comparison function returns an ordering. Flip. Exactly. Exactly.
Have we joked about just using reverse sort?
You could do that too. That would also work. And it's the same asymptotic complexity fact.
Yeah.
It's just O of n, so who cares? I mean, sorting's already n log n.
I'll reverse that.
Although if you're doing a lazy sort, then you're screwed.
Yeah, that's true.
That implicitly assumes that it's a proper comparison where, compare x, y being LT means compare y, x is GT, which it absolutely should, but, And finally, there's on. The type signature itself doesn't necessarily tell you what it's good for, but what it allows you to do is pass in the regular compare function and then like a key function. So you want to sort on a specific key. You do on compare that key. Of course, a more natural way of expressing that is with the infix on. So that's what I do, compare on length. And that will give you the comparison that uses length instead. So if you sort by compare on length, this list of strings, now the short strings are the least and the long strings are the most. So that's how you sort with an arbitrary key. And we're done. So this is probably the longest of the lectures so far. Tomorrow or Thursday, because Wednesday I'm going to be at Lambda Jam. Thursday we'll talk about type classes, and then next week we will attack Mount Monad. Any questions?
I had a question about one of the slides. It was like the slide right before it.
Yeah, of course,
the one
thank you.
titled Loop Fusions. It's a ways back.
Yeah.
I think maybe it was long before that.
You dropped your wallet on your chair, right?
Yeah. So what are those respective functions trying? Like, what were they trying to do? I'm just trying to wrap my head
Take
around
one
what's going
wallet.
on.
Okay.
So actually, I remember what my question was now. Okay, so is it trying to apply in the one on the right? So are they equal? The one on the left and the one on the right, they're both equal, right? Like
If
they're doing
they're-
the same thing.
If there are no side effects, that's
If there
true.
are no side effects, they're doing the same thing.
The one on the right is faster because you only have to pass over the list once.
So you're mapping, okay, so you're mapping G on all the X's, and then you're mapping F on the result of that, right?
Yeah,
Okay.
which means you're doing 2 passes, so it's slower. So
Okay.
if you can,
So then how does that optimization work then? So it's mapping, so the F, the period, like
composition,
composition
yeah.
reverses the order of operations.
Well, no,
right?
so f dot g is the function that does g first and then does f.
Yes. So then, so how does that work out for mapping G on the X's first?
So f dot g is the function that takes an x and computes f of g of x, g being first. So the g happens first and then the f. The ordering is not changed of the f and g in either expression. The g happens before the f.
So I guess what's confusing me is how is the mapping happening twice?
Okay, so in the first one,
Sorry.
no, that's a good question. In the first example, we have this list of x's, and then we map a function g on it, and we return a bunch of whatever g returns. Just call them g's.
Yeah.
And that's one loop over the list. And then we map the f on it, and we do And so that's another pass over the list. So we're passing over the list twice. And the list may be very large. It may be too large to fit in memory, so we're loading it from disk and processing it. And the form on the right, we're saying, okay, what we're really doing is we're applying the compose of these two functions to the x's. So we can traverse the list only once by doing the g and the f on the element at the same time. So first we compute g of x, then we compute f of that, and then we move on to the next element. And that way you only have to do one pass over the list.
So it's not mapping multiple times. Okay, so it's
Yeah.
it's only mapping once now because
Exactly.
So how did you know? I guess how do we know how do we know that G? So sorry, can I try to say like semantically what I think is happening? So
Sure.
G of F is doing G of F, right? In the parentheses.
No.
It's doing G first and then F.
Yeah, so that's essentially,
What is the /x again? What is
that's a lambda expression. So another way to write that is that f dot g x is f of g of x. So f dot g is a function that takes an x and returns f of g of x.
Okay. Function that takes f of g of x. Okay. Okay, so then on the slide, okay, that makes